Hey everyone, welcome back to Wanna Sci. I'm James, and today I'm super excited because we're diving into something you probably never thought twice about. Glass. Yeah, the stuff in your windows, your phone screen, your coffee table. But here's the wild part. Scientists have been arguing about what glass actually is for over a century. Dr. Pulse, please tell me this isn't one of those is water wet debates.
James, I wish it were that simple. Glass is genuinely one of the most fascinating mysteries in physics. We use it every single day, yet we still don't fully understand its fundamental nature.
Wait, seriously? We can send rockets to Mars, but we can't figure out a window?
Exactly, and that's what makes it so intriguing. The question that's haunted physicists for generations is this: is glass a solid or a liquid?
Okay, I'm gonna stop you right there, Doc. Glass is obviously solid. I mean, I can knock on it. It doesn't flow like water. Case closed, right?
That's what most people think, James. But let me ask you something. What makes something a solid versus a liquid?
Solids are hard and keep their shape. Liquids are flowy and take the shape of their container.
Good start. But here's where it gets tricky. When we look inside most solids, like metals or crystals, we see atoms arranged in perfect repeating patterns. It's like a beautifully organized army.
Like soldiers in formation.
Precisely. But when we look inside glass, the atoms are jumbled up randomly, just like in a liquid.
Hold on. So glass looks like a solid, but its atoms are arranged like a liquid? My brain is already hurting.
Welcome to the glass transition problem. This is why some scientists call glass a frozen liquid or an amorphous solid. It's stuck between two states.
Okay, but I've heard this crazy story about old European cathedrals. The glass in their windows is supposedly thicker at the bottom because it's been slowly flowing down for hundreds of years. Is that true? Is glass secretly oozing down our windows right now?
The famous cathedral window myth. This is actually a perfect example of how scientific misconceptions spread. For decades, even professors taught this in universities.
So it's not true?
It's not true. Recent research shows that for glass to flow noticeably, you'd need billions of years. We're talking about atomic movements of just a few nanometers over that time. Medieval cathedrals are only a few hundred years old.
Then why are those windows thicker at the bottom?
Medieval glass-making technology. Back then, craftsmen couldn't create perfectly uniform glass sheets. When installing these uneven panes, they simply placed the heavier side down for stability.
So we've been blaming gravity when we should have been blaming medieval manufacturing?
Exactly. It's a reminder that even scientists can fall for compelling stories.
All right, so if glass isn't flowing, what is it doing? And why can't scientists just agree?
The real mystery is the glass transition itself. Imagine you're cooling down a liquid. Normally, atoms would arrange themselves into neat patterns as they slow down, forming a crystal.
Like water freezing into ice.
Perfect example. But if you cool certain liquids really fast, the atoms don't have time to organize. They get locked in place while still in their random, liquid-like arrangement.
So it's like a game of musical chairs, but the music stopped so suddenly that everyone froze mid-chaos.
That's a brilliant analogy, and this frozen chaos is what we call glass. The atoms want to organize, but they're trapped.
Okay, this is blowing my mind. But why does any of this matter? Who cares if glass is solid or liquid if it works fine?
Great question. Understanding glass transition could revolutionize material science. Think about it. If we truly understood how materials freeze in disordered states, we could design better plastics, stronger metals, even new types of computer memory.
Whoa, so the answer to the century-old debate could unlock future technology?
Absolutely. Plus, glass transition appears in everything, from polymers to proteins. It's a fundamental phenomenon we still don't fully grasp.
All right, my Wanna Sci viewers, drop a comment. Did you think glass was slowly flowing before today? Be honest. Now, Dr. Pulse, let's talk about something I notice every day. Why is glass transparent? I mean, most solids you can't see through at all.
Another excellent question. To understand why glass is transparent, we first need to understand why most materials aren't. Take metals, for example.
Yeah, like steel or aluminum. Definitely can't see through those.
Right. In metals, electrons can move freely throughout the material. When light hits metal, these free electrons absorb the light's energy and re-emit it immediately.
So the light bounces back instead of passing through?
Exactly. That's why metals are shiny and reflective. The light never gets a chance to travel through them.
Okay, but glass doesn't have these free electrons.
Correct. In glass, electrons are tightly bound to their atoms. They can't roam freely like in metals. So when light enters glass, something different happens.
The light just passes through?
Mostly, yes. But here's the fascinating part. Glass atoms have specific energy levels that electrons can occupy. For visible light to be absorbed, it needs exactly the right amount of energy to bump an electron from one level to another.
Like climbing stairs. You can't stop halfway between steps.
Perfect analogy. In glass, these energy steps are too tall for visible light photons to climb. So most photons just cruise straight through without interacting.
Wait, most photons? What about the others?
Occasionally, a photon does have enough energy to excite an electron. When this happens, the photon gets absorbed temporarily. But then the electron falls back down and releases a new photon with the same energy.
So even when photons get absorbed, they get replaced by identical twins?
That's a fun way to put it. The result is that light passes through glass almost unimpeded.
This is so cool. But I've heard glass isn't transparent to all types of light. Is that true?
Excellent memory. Glass is transparent to visible light, but it blocks ultraviolet light quite effectively.
UV light? Like the stuff that gives you sunburn?
Exactly. UV photons have more energy than visible light. That extra energy is enough to excite electrons in glass. So UV light gets absorbed rather than transmitted.
Wait, that means glass can protect us from UV rays?
Absolutely. In fact, there's a famous story about physicist Richard Feynman.
The Feynman? The bongo-playing genius?
The very same. During the Trinity nuclear test in 1945, everyone was given special dark goggles to protect their eyes from the intense light and radiation.
Let me guess. Feynman did something crazy?
He sat in a truck and watched the explosion through the windshield with his naked eyes.
What? That sounds incredibly dangerous.
Most people thought so, but Feynman knew that glass blocks UV radiation. The windshield would protect his eyes from the most harmful wavelengths.
That's either brilliant or insane. Maybe both?
Feynman had such confidence in physics that he was willing to bet his eyesight on it. Fortunately, he was right.
That's the kind of trust in science I aspire to. Though maybe I'll start with something less explosive. Hey, Wanna Sci fans, would you trust your knowledge enough to try something like that? Let us know in the comments. Okay, Dr. Pulse, I've got another question. Why does glass break so easily? I mean, it seems strong, but then you drop your phone and boom, shattered screen.
This actually ties back to glass being an amorphous solid. The random atomic structure that makes glass transparent also makes it brittle.
How so?
In crystalline solids like metals, atoms are arranged in regular patterns. When you hit a metal bar on one end, the vibration travels smoothly through the organized structure.
Like dominoes falling in a line.
Great visual. This organized structure allows metals to distribute stress and deform gradually. They can bend before breaking.
But glass doesn't have that organized structure.
Exactly. In glass, atoms only interact strongly with their immediate neighbors. There's no long-range order to distribute the force.
So when you hit glass, the force can't spread out?
Right. Glass resists deformation rigidly until suddenly, catastrophically, it reaches its breaking point.
It's like glass is the stubborn friend who refuses to bend on anything until they completely snap.
That's actually a very accurate comparison. Glass doesn't give you warning signs. It seems fine, then crack.
So how do we make glass that doesn't break, like bulletproof glass? That stuff is incredible.
Bulletproof glass is a masterpiece of engineering. Let me explain with a thought experiment.
I love thought experiments.
Imagine you're lying down, and someone places a thick, soft mattress over you. Then they put a steel plate on top of the mattress. Now, if someone hits the steel plate with a hammer, what happens?
The plate is hard, so it won't dent easily. But the mattress underneath would cushion the impact?
Exactly. The steel plate distributes the force over a large area, reducing pressure. Then the mattress extends the stopping time, which reduces the impact force even more.
So you'd barely feel it.
Precisely. Bulletproof glass works on the same principle. It's made of multiple layers alternating between hard glass and soft plastic.
So it's like a sandwich?
A very tough sandwich. The hard layers distribute the bullet's force, while the soft layers absorb energy by deforming. Together, they stop the bullet without shattering.
That's genius. What about phone screens? They use something called tempered glass, right?
Yes, and tempered glass is fascinating too. It's created through a special heating and cooling process.
Sounds complicated.
It's actually quite clever. Glass is heated to high temperature, then the surface is rapidly cooled while the interior is still hot.
Why would that make it stronger?
When the surface cools quickly, it solidifies first. Then, as the hot interior cools and contracts, it pulls inward on the already solid surface. This creates compression stress on the surface.
And compression makes it stronger.
Exactly. The surface is now under constant compression, so external forces must first overcome this built-in stress before the glass can break.
So it's like the glass is already flexing its muscles ready for impact.
That's one way to put it. This is why your phone screen can survive many drops that would shatter regular glass.
Though not all drops, sadly. Speaking from experience here.
Nothing is indestructible, James.
Fair enough. Now, I've noticed glass comes in different colors. Like beer bottles are brown, wine bottles are often green. What's up with that?
Color in glass is all about additives. Pure glass made from silicon dioxide is actually colorless.
So the colors are intentional.
Absolutely. Different metal ions added to the glass mixture produce different colors. Iron creates green or brown tints. Cobalt produces deep blue. Copper gives turquoise or red depending on oxidation.
So it's like dyeing glass?
Similar concept. But here's the interesting part. Those brown beer bottles aren't just for aesthetics.
They actually serve a purpose?
Yes. Brown glass blocks more UV light than clear glass. UV radiation can break down compounds in beer, creating that skunky flavor.
Oh no, nobody wants skunky beer.
Exactly. That's why premium beers often come in dark bottles. It's functional design.
So next time I'm at a bar, I could impress people with my knowledge of UV-blocking beer bottles.
You absolutely can. Tell them Wanna Sci that you.
Will do. All right, Dr. Poles, we need to talk about something that's been bothering me. When light goes through glass, does it slow down? Because I learned in school that light travels slower in glass than in air. But you also said light always travels at light speed. Which is it?
This is one of the most commonly misunderstood concepts in physics. Both statements are true, but we need to think carefully about what we mean.
I'm listening. Carefully.
Individual photons always travel at the speed of light. They cannot slow down or speed up, ever.
Okay, but then why do textbooks say light slows down in class?
Because we're measuring the average speed of many photons traveling through glass. Some photons zip straight through without interacting with atoms.
And others?
Others get absorbed by atoms, which briefly excites an electron. Then the electron drops back down and emits a new photon.
Like we talked about earlier.
Exactly. Now, this absorption and re-emission takes time. During that time, there's no photon traveling forward.
It's like the photon took a little break.
Perfect. So if you track one photon, it always moves at light speed. But if you average all the photons, including the ones that took breaks, the average speed is slower.
That's such a cool explanation. So light doesn't actually slow down. It just takes more coffee breaks in glass than in air.
I might steal that explanation, James.
Be my guest. All right, we've covered so much today. Glass is this weird in-between state that's puzzled scientists for over a century. It's transparent because of energy levels, it breaks easily because of its random structure, and light doesn't slow down, it just takes breaks.
You've got it. Glass is one of those everyday materials that, when you look closely, reveals incredible physics.
I'm never looking at a window the same way again. Dr. Poles, thank you for another mind-expanding conversation.
The pleasure is always mine, James. Science is full of these hidden mysteries waiting to be explored.
And that's what we do here at Wanna Sci. We explore the science hiding in plain sight. If you enjoyed today's episode, please hit that subscribe button. Give us a thumbs up if glass blew your mind. And definitely turn on notifications so you don't miss our next adventure.